Okay, today's problem is the fourth problem of the jump game. So what it is given here, it is given an integer array. You will be like you will start from the first index of the array, 0th index. So what you can do, you can you go to the exactly next step or the previous index, or you can jump to any index j where ARR of I and ARR j are equal value, and but I and j are different. That means self loop doesn't exist. Apart from that, you can jump anywhere. So we have to return the minimum number of steps uh, we have to take to reach the last index. And the thing is, obviously, you cannot jump outside the array. It is not possible. So what is the constant? Constant are 4 length, and value is here minus 10 to the power 8 to 10 to the power 8. Okay, fine. If you remember, this is the exactly kind of same kind of problem with minimum jumps to reach the end via time teleportation. It is kind of exactly same. There you have to calculate the prime number. Here I don't have to calculate the prime number. Instead, we have to check what is the error of I and error of j. Like in what indexes, in which indices, like values are same. You have to calculate it. Apart from that, everything is same. Anyway, like if you want, you can do solve this problem as well. Exactly same problem. Okay, let's see what the problem is. So earlier we can like here in this index, 0th index. Okay. So let me also mark the index. Okay, let's also mark the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is the given here? I am in this position. I have to reach at the last minute. What will be the easiest part to do that? I can jump consecutive index of this, and this. So total 9 steps are required. So can we reach less than 9 steps? Yeah, I can do. If you see here, from here I can jump in 100 because they have said I can jump to any index j if both values are like value of the ith index and value of the j index are the same. So then I can jump to here. I can go to the previous index, and here I can jump to the last index. So total 3 steps I can jump. Right. Now again, it seems like a kind of see. There should be some connectivity. So if you watch in the basis of connectivity, what can you see? Like from 100 to 23 you can go, 23 to 23 you can go, 22 to 404 you can go, 404 to 100 you can go, here you can go, here you can go, here you go. Just the kind of there internally there is a path like from every index you can go forward, you can go backward. There is a path. So now there are some special paths like this 100 to this 100 you can go. Similarly, it's vice versa. From 23 from 23 this minus 23 to this minus 23 you can go, and also you can go this minus 23. So vice versa path are there. So if I do again, don't want to remove twice. This one to this one you can go. Then this minus 23 to this minus 23 you can go. This minus 23 to this minus 23 you can go. Okay. And what this 404 to 404 you can go. And there is another, and again another path is from this 23 to 23. These are kind of a path. So you can say it's a kind of a graph related problem. And this graph related problem, what they have asked me to traverse from 0th index to the 9th index. Correct? And like now, like if you don't think is a starting point, or like you can think is a starting point and ending. You don't think is it a starting there, like starting index and ending index. Don't think of that. Think of a one start point, one end point. And in a graph, you have to find, if you need to find the minimum distance of 2 points, what is the best algorithm to that? The algorithm is to use the BFS algorithm. So the BFS algorithm you all know, like we have to start and we have to visit all the adjacent points, and after that we can go to that point and check all the adjacent points. This is how we do the BFS, right? Here also you have to apply the BFS. But we especially need the adjacency nodes, right? List of adjacency. Like from 100, where can I go? From 100, I can go here or there or there. Like here or here. What are the options? Here I can go here. I can go here. Like for especially for, let's say, for this 404 here. I can go here. I can go here. I can go there. So there are this kind of paths are there. For 23, where I can go here, here. These four paths are there, right? So I need this adjacency list. So hotel, like right now we can't build adjacency node for each and every case. We know one thing, from one particular index we can go left side and right side, right? This is fixed, so we no need to, anyhow we need to check that condition. And apart from that, where I can go the exact same values, like wherever the same values are present, I can go back to there. So what I can do, I can iterate through the list. I can iterate through the list, and I can store this value in a map or dictionary, and I can find out then which index position it is present there, and I can use that thing in the while calculation. Okay, okay. Let's see what we could do. Can we use this thing? Minimize this and this. Okay, I guess this is enough for me. Also remove this part and move right. Okay, yes, this fine. So let's see what is my function. My function is like min jump. Let's see, min jump, and what is given? Obviously, error is given. Okay, let's start. First, as always, we need the number of the length of the array. N equals to error dot length. Okay, I can find the length. Cool. After that, what I need? As I told you, I need to calculate like what are for the same value in which indices, in all, what are the indices, and the same value is present. Correct. So I need a map, one has map MP, uh, one has map. Let's say has map, or map, whatever it is, has map MP. Will initialize this thing, like every element of the hash map will be kind of what? It is a integer and one list or a vector. Okay. So I am indicating like hash map int, it's a list or an array. This is the I am indicating. Hope you understand. Like I have to create one and hash map value will store integer, and the like value will be key will be integer, and value will be one list or array list or vector, whatever. Okay, let's get it. So now I have to iterate each and every index. So for that, select for int I equals to 0, I less than n, I plus plus. If that is the case, what I have to do, I have to simply do what? Include MP of not I have to store the value. P will be my value. MP of ARR of I dot add append, whatever it is, pushback, whatever it is, ARR dot I add what? I have to add the index, in which indices the same value is present. That is what I am going to do. Okay. Now my next step is what? Now I have taken uh, I have already done the adjacency position of the each and every value. Like what I actually want to do. Like I have already calculated in which indices that same value is present. Okay. So right now we have to start the BFS. So in the BFS, we all know we need a what? We need one visited array. One visited array. So I need a visited. So visited equals to, let's say, one vector array list, whatever. Um, it is one array list I'm saying. Array list or array is actually fine here. So array array of y, array of my visited visited of size, what size my in, okay, size my in, and initialize everything with 0 or false or anything, right? So I'm saying about 0. Okay, 0 means false, 1 means true. So earlier at the initially everything is, but everything is false, so that is not visited. So now what I have to do, I have to iterate. Like now in this BFS you also need a queue. Let's initialize the queue as well. So queue equals to, it's nothing but a queue, initializing a queue, and I have to do what, I have to add the queue, add the, like we have to start from 0 to index. So 0 index I have to add into the queue, and mark this 0 as visited because I have already visited the 0, right? So queue dot add, I have to add into the queue, and this queue is nothing but what, um, queue add. Now here what I have to do, I have to add, I have to that index, I have to add this index, and this, to add this index, one another thing I have to add also, like I, what is the number of steps I need to reach this index, I need to reach this index. These are the things I also have to overwrite. So I am not only adding the index, I have to also add the number of steps to reach the index. So what I am writing, that is 0, one thing. So better to add an array or vector or to length of array, it is better. And what is the minimum limit? So I can jump to 0th index with the 0 step, right? So this is initial provision. So I can jump to 0th index with the 0th step. So that's why I think 0 0. And as I told you, like I have to do visited of 0 as I visited the thing, and I visited that 0 equals to 1 because I have already marked as visited. And after that, I have to write a while loop here. Correct. I have to write the while loop in this position. While loop in this case. So it will take some space. So better to write a function so that I can do side by side. So I can do what? I can write a function. Let's say BFS. What I have to pass here? This function, if you take the global, you don't need to pass anything, you can just pass the, you don't need to pass anything. But if it's not a global, many things you have to pass. Past is obviously ARR. ARR, you can pass in or calculate in every time. I'm passing in. Okay. And also I need what, I need map MP, where I'm storing the, at the, like same, in which you need the same values are present map. And what I can do, and again I can pass the queue here, pass the queue here. So this is my BFS. Okay. Okay, let's see what we'll do after that. So this is what we'll do, simply run the BFS. Okay. And right now, okay, let's write save this part here, and I will write the BFS code here. Okay, for BFS code, what I have to do? Okay, so let's write the BFS code in this case. Like function BFS, BFS. What is passed here as earlier, ARR in my map and my key, that is BFS. So simple, like BFS, how long we run the BFS until my queue is not empty. That still then I have to run the BFS. So for, or not for, while, until while my queue is not empty. So not equals to queue dot is empty. Until that is the case, I'll run my BFS. Correct. And what I have to do is that I have to do, so I have to first take the front element like in the queue. So let's add the, so the queue here, this is my queue. In the queue I have added 0 comma 0, 0 comma 0. So what I have to do? So I have to put that queue here. I have to like pop this front from the queue, right? I have to pop this front right the queue, and I have to check this index from this zeroth index where I can go. Okay, so let's do one step at one time. So what can I do? Like I need like item equals to q dot front or q that pop front or whatever the function is, q dot pop front. So from here what I need, like what I can calculate, I need what? I need index idx. It is nothing but item 0. And what is the jump? Jump is nothing but my item 1. So these are the two cases, item 0 and item 1. Okay, so right now what we could do, like now what I have to do. So if my index is already in -1, I can return, right? I can return that value. If that is not the case, then I can travel to this side or this side or any other place, correct? So simply I'll put a if condition. If my index equals to n-1, then what? I have to return number of jumps I have taken. So return the number of jumps. So number of jumps. How good I get it? This jump variable is the number of jumps, because see, this zero is represent like how many jumps I need to take to reach this index position. So this is the thing, right? So I'll return what? Return the jump, correct? So after that, if that is not the case, then I have to check, can I go to the right side, can I go to the left side, or what are the places I can go, correct? So this is that thing we have to write. So let's write one by one. I need some space, so let's move in some places. Okay, I guess this is fine. So what I could do, I could so I write if statement. So if I have to check, let's start from the left side. Can I go to the left side? Can I go to right side? Or can I out of the other places? So left side means index -1. So going to left side, that index must be valid, right? So I have to check if index -1 is greater equals to 0. If that is a valid index, then only I can jump, right? So another thing I have to do, if it is already not visited, if it is visited, I shouldn't go back, because if it is already visited, that means like I'm coming here, but at this place 23. If I think about 100 to 23, I have already come. Now 23, I have to check from what are the cases we can go. These are the cases we can go. So whenever I am checking that 100, this is already visited, right? This 100 is already visited, so I cannot go back to there. So I have to check like whether it is visited or not. If it is not visited, then only I can jump. Okay. So what the condition? If it is greater than 0, and if my visited of index -1 is not equals to 0. Sorry, equals to 0. That means not visited. Equals to 0, not equals to 1. So if it is not visited, then only I can jump. So jump what? So jump. So that means jump. What I could do? I'm going. That's it. Right? So I have to write like I have to append. Like that time I have to append the next element to the queue. Correct. So here for this index, I assume I am in the 23. So I can add 100 or I can add 23, whatever it is. Okay. So whatever I'll do. Okay. Before that, this 00 is popped out, right? 00 is popped out. That case, so that is the case. If that is the case, I will add what? I will add my this thing. Means q dot add what? My next index to which I am going to jump, idx -1. Okay, and then what is the jump I need to do? So earlier jump plus one jump I have to take. whatever already have, like what jump I need to reach at this current index. Assume this one, this 100. What jump I need to get, like need to reach this index plus one, go to the left side or right side, right? That's why index minus one. I'm going to index minus one with a jump of jump plus one. So that means number of jumps to reach here plus one jump. Correct. This is what I'm doing, and I am inserting into the queue. That means this is already visited, right? So I have to make this thing as visited equals to, so visited of index minus one. This is already visited. That means mark as one. Correct. I guess you get it. Now, whatever it is go, like for if we consider from here, nothing is going to add here. Correct. So it is, let's to the next case. Let's move it here. Reduce this one. Move here. So if that is the case, like if my index plus one, this could be out of range, my out of index, so I have to check it is less than n, and the next thing will be exactly kind of same. All will be exactly kind of same. Something just my it will be instead of index minus one, it will be index plus one. This is what. So I have to check, like if visited of I plus 1 equals to 0, if it is not visited, so I will add index plus 1 into the queue and jump plus 1, and I have to mark this index visited of index plus 1 equals to 1. So that means if I am here, I can go in which places I can go. Left side is not a valid index, so I'm not going to add. It is a valid index, so I have to do what? In this here, I will do what? I can go index 1, the jump 0, this is 0, 0 plus 1, that is 1. We can go index 1 plus 1. Okay, this is the this jump I can take. This jump I can take. Correct. Okay. So what are the other cases? Other cases I have to check if that whatever the item present inside my map, what are the index it is the map, I can jump that as well. Inside there I can jump as well. So I have to do what? Another for loop. For loop for what? For each and every index I inside the what? Inside the np of map of, in the map how we're going to store. I'm going to store integer. It is pointing to a list or array list or vector. Okay, so this integer is nothing but is the value, this is value. So right, okay, I guess you get it. So in that case, uh, what will be the here? I have to write here mp of nothing but my arr of index, arr of index, error of index. Correct. So I have to iterate for each and every value of this error of index. So I have to check where it is present, whatever it is present I have to add into this. So before that I have to check one thing again. I have to check whether this index and this index should not be same. Like whatever, like say that this 3 is present only once, so that is 8. Whenever I am searching this loop, 3 will give us 3, and like index will be 8 and current index will be 8 also. So that thing I have to check, the index should not be same. Okay, so I have to check if my index are different, like I not equals to I not equals to my index. If that is the case, and another thing, and if it is not visited again, so it is again, if it is not visited, if it is not visited, visited of I is equals to 0. If it is not visited, in that case, what can I do? Simple, the same step I had been here. I have to append into the queue the jump plus 1. Correct. Append the jump plus 1. Copy and paste. Again, append another the jump plus 1 and mark visited, like you mark this thing as visited. Okay. So here I no need to do this. I have to I is only 5. I is only fine here, not index plus 1, it is only I, and those are fine, I guess. So this is the case I have to do. Okay, I didn't done a mistake here. I have to add close the bracket. This place is fine, and let's see. Okay, so let's close the bracket here. Then close this bracket. Close the bracket here. Then close this bracket. Okay, and visit rate of what? Visit rate of I equals to 1. Correct. So this is what this here this if statement ends. Here this for loop ends, and uh, here this above while loop ends, and the function also ends. So see, this graph is always like these 2 points are always reachable. At the worst case, what you have to do, you have to jump each and every case, right? This is the worst case you have to do. So anyhow, it is reachable. So explicitly, we don't want to return -1 on something because anyhow it is reachable. You know it will be reachable in some point. That's why return jump we'll find here. So anyhow, it will come to this one. It will return jump, and this is the my minimum jump. And this is my target position, right? So this return jump BFS also return this jump. I need the answer. So I can simply write here also return this BFS. I can simply jump this return. I hope you get it. So let's see with the dry run. Let's start with the dry run. So in the dry run, I have okay. Let's do the dry run in the middle. I guess you can see it properly. Okay. So let's start. So I'm calling BFS at the 0th index. I'm calling BFS at the 0th index. So my queue becomes 0, comma 0. Q becomes my 0, comma 0. Okay. At the end, like after that, I'm calling like adding to the 0, 0, then visit 0, 1. Then I'm calling the BFS of that index. Okay. So BFS, and while my queue is not empty, I have to iterate. The queue is not empty. So whatever the first thing I have to pop the front element. I have to pop the front element and store index 0 and jump 0, right? Okay. So also initialize index and my jump. Okay. So I have to pop. This is popped. So index will be 0. There will be 0. Now here I have to check whether it is my n minus 1. No, it is not my n minus 1 because it is 0. N minus 1 is 9. So I cannot jump. Sorry, I cannot return anything. So what I have to do, I have to check whether I can move to the left side. I can move to the left side. Is it? No, I cannot move because it is 0 minus 1 is invalid index. But I can move to the right side. So I will do what? I will add into the queue. So I will add right side is 0 plus 1 is 1, and jump is nothing but 0. This is 0 plus 1 jump I need. Okay, plus 1 jump I'm going to need. And earlier my visited array. So visited array, what was there? It is my ninth one, 1, 2, 3, 4, 5, 6, 7, 8, 9. So earlier everything is false, so that's why I'm not marking anything. I'm just marking that if it is blank, think it is a false. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so initially I put 0, add 0 and mark this thing as visited. Okay, so I'm marking this one as visited. After that, at the 0 index I pop, then I can say I can go to 1, 1. So 1, 1 is already now visited. 1, 1 is now visited. So with the value of what? With the value of 1. So 1, 1 I can visit. Now let's see, this is done. These two cases are done. Now see what are the hundreds are present. So I can iterate to the map of 100, and see in which indices 100 is present. So this 100 is present as 0th index and the 4th index. So it will map of 100 starting 0 and 4. So if I iterate and if I check like if it is like I have to include all the indices which is where 100 is present, but it is already 0 is 0, 0 is there, current index is also 0. So this is the case, like it is like the my next index should not be my current index. So I'm checking here, and then I'm checking that whether it is like first case is failed, next case becomes 4. So it is 0, this is 4, and this is 0. So both are not same, and my index 4 is not visited. So I'll do what again? I'll put this fourth index, and jump is what? My current jump plus 1, current jump is 0, and plus 1 means 1. Correct? So this 4 will be right now visited. Okay, fine. Now this loops end, and I will check again if the queue is empty or not. If queue is empty, that means everything is visited. So queue, like right now in the queue, 1 is present. So I will pop this 1 and index become 1, and jump becomes what? Jump becomes 1. So on this 1 1. So this 1, the first index where I can go 0th index, I can go sorry, 2 index, I can go the 6 index. So first thing I have to check index -1, it's a valid. Yeah, it's valid. And if it is not visited, see here, if it is not visited, but see here, it is already visited. Index of 0 is already visited, so I cannot add here. So I have to check class 1. Class 1 means 1. Second, it is valid. Yes, valid. So what is it is visited? It is not visited. 2, it is not visited. So I can do. So I can add that thing. I can add what? I can add my second index. That is my second index. And what is the minimum step I can go? Like current jump plus 1 jump. So 2. Current jump is 1, and plus 1 is 2. So that's why 2. Okay, fine then. Fine, it is done. So I have to also mark this as visited. So 2 I have done, so I mark this as visited. So next, where I can do, I have to check like is there any case where I can jump. So you can see here it is present as like map. So 20 minus 20 present in which places? First index, second index, and the sixth index. So map. So what will map of minus 3 stores? Map of minus 3 stores is 0. Sorry, not 0. 1, 2, and 6 index. So I have to iterate each and every index. First I am coming to 1. So 1 is actually equals to 1. That is not, should not be the case. So I cannot go to the first index, like this 1 index. Next thing is 2. 2 is not equals to 1. Good thing I can jump to 2. But the thing you notice, like 2 is right now already visited. 2 is not like the flag of the 2 is already visited. See, 2 is already visited. So I cannot also go to the 2. But I can go to the 6 index. Like I can go to the 6. So what I'll do, I'll simply include 6 with the cost of what? With the cost of like current jump plus 1. So jump will be 2. Okay, good thing. It's done. Now anything present? No, nothing is present. So loop ends. I go back to queue is empty. No empty. It's there. So I'll pop that next element. So 4 1 I will pop. So index become 4, and jump will becomes 1. So this is the fourth index means this one. From in this place where I can go. Can I go to the left side 404? Yes, I can go to the left side. It's a valid index and not visited because 3 is not visited. Okay, earlier I forgot. This 6 is also visited. Okay, so 4 is not 4 minus 1 is not visited, so I can add into it. So I can add what? I can add 3. What is the cost? 1 plus 1, that is 2. I can write it here. Okay, I can write it here. And can I go to the right side? Sorry, I can go to the right side. From here can I go to the right side? Yes. 5 is it visited? No, it is not visited. So I can go to the right side. So I can also move to the 5 with the cost of 2. So what I did, I have visited 3, and now I can visit a 5. I'm marking those as visited. Okay. So these two cases are done. Now I have to check what are the 100 is present. 100 is present as a 0th index. So map of 100. What will it will store? It will store map of 100 will store 100 0 comma 4. Can I go to 0th index? Yes, I can go because it is not equals to my current index. But when I went checking it is, I can go to 0th index. I can say visited. It is already visited. It is already visited, so I cannot go. So I have to skip this 0. A fourth case, this is the index and current index, and it is actually equal. So I cannot go to the this fourth index as well. So this loop also, and I will not add anything here. So if my like while queue is empty, is my queue is empty? No, there are multiple steps are there. So 2 from 2 I'll pop. So I'll pop simply 2. So this becomes 2 and this becomes jump, it becomes 2. From 2, where can I go? From 2, where can I go? I can go to left side, right? And left side is 1, 1, 1, 1. It is valid index, but it is visited. It is, you can say, is it visited or not? 1 is already visited. So I cannot go to the first index. Okay, let's see the next case. Next case is nothing but index plus 1. Index plus 1 is what? 3. You can see 3 is already visited, so I cannot go to the third index as well. Okay, so minus 23, what are the places minus 23 present? 1, 2, and 6. If you notice, 1 is already visited, 6 is already visited, and I cannot go back to the 2 because it is a own index. So I cannot go anywhere. So from these, I can go actually three places, 1, 3, and 6. So 1, 3, and 6 all are visited. So I cannot go anywhere. So I'll not add anything from this queue. Okay. Now my next element is nothing but my 6. This 6 comma 2. I will pop 6 comma 2, 6 and 2. Okay. From 6 and 2, where can I go? From 6 I can go to a left side. For left side means 5. 5. So I have to check 5 is a valid index. Is it a valid index? Is it visited? Yes, it is visited. So I cannot go. Okay. From 6 to 7 I can go. 6 to 7 I can go. 7 is valid index. Yes, it is a valid index. Is it visited? 7 not visited. So I can add. I can add the 7th place. So we'll add 7th index. How many steps I can go to 7th index? With the cost of 3. With a cost of 3. Current is 2. 2 plus is 3. Cost of 3. I can do. Okay. 7 index I can go. With the cost of 7 index. With the cost of 3 I can go. So 7 is done. From what are the cases? 6 is again nothing but 1, 2. It is already visited, so I cannot go on the same place. So 6 is done. So now I have to pop. What? 3 comma 2. Correct. So I have to pop 3 comma 2. So that I have to pop. So 6 will be 3 and this becomes 2. The 3 comma 2, what are the cases? 3 comma 2 is here. So can I go left side? 2, okay, 7 mark as visited. 7 mark as visited. So 3, can I go to left side? 2, it is valid index, but it is already visited. I cannot go the left side. Can I go right side? 4, yes, right side is a valid index. 4, it is already visited, so I cannot go to the valid index. What are the yes I can go? I can go the I can go to the other place where my value is same but index is different. So what this 404 actually contains two indices. This 404 is currently 3 and 9. 3 and 9. Can I go to the 3? No, because my target index is same as my current index, so I cannot go to 3. Can I go to 9? Yes, I can go to 9. I can go to 9 and I can move to the 9. So I can add the 9. So what I can do, I can add to the 9. So see, even though I'm getting, I can see it's a target index, right? But still, I am not doing anything. Let wait and see what will happen. So I'll add 9 into where? Into mine where with the cost of 3. Current jump is 2. 2 plus 1 is 3. So 3. Correct. So that we could do. Okay, fine then. Then anything left? Nothing. So I can next I can go to the 5 comma 2. So 5 comma 2 I can pop out. So this becomes 5, this becomes 2. From 5 to 2 I can go. From 5 I can go to where? I can go to left side, right? It already visited. 6, it is already visited. And another space it is 7. Okay. 7 is already visited. So 5 comma 2 will not create anything. So 5 comma 2 is done. Then I can go to 7 comma 3. 7th. From 7th, where can I go? 7 to go to 6. 6 is already visited. I cannot go. Think. Okay. If you remember, like I visited 9. Mark 9 as visited. Okay. So, okay, whatever it is, like 7 from currently 7. 7 to 6 I cannot go because 6 is visited. 7 to 8 I can go and 8 is not visited. So I can write is as 8. 8 with the cost of our current is 3. 3 plus 1 is 4. Okay. So that is what we can take. Okay. Cost of 4. So this is done. And after that, from currently 7 I can go to 5th again. because Shiv is same value, but 5 is already visited, so I will not go. So 8 is also visited, so it is done. Okay, now I will pop what? I will pop 9 comma 3. Whenever I am popping 9 comma 3, I can see this 9 is nothing but my target index. So this is my target index. That time I'll return, I no need to check any other thing, I simply return my 3. I can simply return my 3. This is the case. This is the minimal. So this is for the dry run. Okay. Hope you get it how it works. Okay. See, now let me show you one special case. I will show you one special case. Assume like this is my value of my error. Okay. See, this is present 10 to the power 5 or 10 times. Okay, this is 10 to the 4 is our limit, so 10 to the 4 times it is present. See what will happen. I can see. So what will my map contains? This is 0, 1, 2, 3, 4, 5, 6, 7. If I do the dry run here, my map contains what? 0, like value of map of my 7 will contain 0, 1, 2, 3, 4, 5, 6, 7. Okay. So initially my queue, and let's say this is a visited case. So view initially in the queue, I'll inside the queue I'll do what? Inside the queue I'll add 0, comma 0 as always. So after that I'm popping it. So this becomes visited. This become my visited. After that, what will happen? This will be my visited. Now 0 is 0 forbidden. So index will be 0 and what is called my jump is 1. Correct? Correct. Not 1 0. So I pop this index. Now I have to check from 7 where can I go? I can go to that side. So literally from 7 I can go in everywhere, right? That's a single case. For a single case, I'll add what? I will add 1 comma 1, 2 comma 1, 3 comma 1. Like this is what I can add, right? Up to what? Up to 7 comma 1. Include into it. Okay, so this is done. So next step I will do what? I will pop my 1 1. So this like and mark everything as visited. Mark everything as visited. Okay, I can mark everything as visited. But see here, see this case. This becomes 1 and 1, right? This becomes after I pop 1 1, it becomes 1 and 1. So here where to check, I am checking like from 1 I can go left side, right side. I am this is fine. But every time I have to check for this one, even though all are visited, I have to check. I have to check whether everything is visited or not. Like I have to come back here. I have to check it is visited. Like my first intent is I have to add my the places. I have to add the places where I can go. But even if it is not visited, then I will not add it. Okay. If it is already visited, I will not add it. But the thing is, I have to check. Na. I have to check whether it is visited or not. So I have to come here and check. Come here. Come here. Come here. In every case, I have to come here and check if it is visited or not. If it is visited, I cannot go. So every time you can see if it is visited, like still I have to come here and check. So it will be for every item in this list. I have to check for each and every item. So that is already visited. So what I could say here, if I am 7, so should I check like whenever I assume so should I check for every cases? No, I shouldn't check. Think this example like 7 1, 7 2, 7 3, 7 4. So whenever I am here, whenever I am in this place, I have already added this 7 and this 7 into the queue. Correct? I have already added this 3 like this 3 7 into the queue. So when I reach here, when I reach at this 7, should I add should I check these other places? No, because whatever the other places are there actually, this is already added. This is already added my previous item. So when I add all the equal values, whenever I add all the indices where the equal values are present, that means next time when I reach that same equal value, the other equal values are already added into the queue. I need not add the again. I need not add or need not check it again because I knew like if it is present earlier, I have already marked as visited and I shouldn't go and check whether it is visited or not. This is the case. So what I actually want to mean, like here also, if I am getting the 7 thing, I know my earlier is a 7, so I have done already. I have to mark. I have already done the marking. Like those 7s are already visited, so I shouldn't go and check. So it is the easiest way. So this is I can say, but I cannot say to the computer or code like do this thing. So I have to write a logic. Write a logic of what I have MP of 7 I have done. Whenever I already came MP of 7, a map of 7, done. I have done my marking. Then I'll remove this MP of 7, or I can do what MP of 7 I can mark as an empty list. Okay, I can either delete that from my enter MP, or I can do as a marking as a I am clearing or remove everything. So this should be an empty list. If that is the case, then whenever I came next 7, I will check what. Oh, I am coming here and checking what are the indices I can get. I'm getting, oh, it's empty. I cannot go any other places. Right. I guess you are getting it. Like whenever I'm coming here, I'm inserting all other cases and mark this thing as empty. Because yes, see yes, 7. Whenever I come to this 7, I can see like all the other cases are marked. All the other cases are marked. Okay. For this example, assume not all are 7, but here MP of 7 what? MP of 7 will contain like 0, 1, 2, 3, 4, 5, 6, and 7. So this MP of 7 will contain like 0, 2, 4, and 6, right? So see, assume whenever I'm coming this 7 or this 7, I know like 0 indexes will be the same. Na? Indexes will be 0, this will be 2 and 6 if whenever I am this place. So this is already marked as my previous 0, correct? So no need to mark even though I'm coming here. So this 0, 4, and 6 are already marked visited. So I no need to check. So whenever I get like I am iterating each and every item. If I get a unique item 7, and if I am done the adding all the cases, then I will simply remove this case. Like in future, if you get the 7, no need to check your adjacent. So like need to check the adjacent, but no need to check your other indices where the same values are present, because that is already marked before. If it is not, uh, it is not appearing for the first time. If it is appearing for the first time, then only it will store some values. If it is second appearance of the same item, then that the indices where the same items are present are already marked, correct? So that's why whenever I am getting one item, and after iteration, I'll assign this index as empty index. Hope you get it. So what I am going to do, I am to just add only one single line here. Like after the for loop is done, I am marking that I am marking this thing like this map of that index, my initial index that I actually popped, initial index that I actually popped from the queue. All I have, I that means there are two cases that in the MP. There are two cases of for this index. One case is this is the first time the value of this index is appearing first time, or there is another case the value of this index is appearing second times or later. Like fast appearance is also done. If it is fast appearance is done, there should present some indices that indices I have to add into the queue. If it is appearing second times or more, that means I have already added that appearance earlier whenever it appeared first. Now I no need to check, because now I can do that this is empty of index equals to, I can initialize with the empty array list or list, that I can do. Okay. I hope you are getting it. This is the case I am to. So this is all about this problem. Okay, let's talk about time complexity. Time complexity, I'm iterating only once, so it's a big O of n. And for BFS, time complexity is big O of number of vertex or node plus the number of edges. So anyhow, number of edges could be in a big O of n only, and this vertex is nothing but big O of n. And this is also, if we ignore or not ignore, it's also big O of n. So that BFS is also done by big O of n order. Okay, so even if it is a complete graph, in the complete graph, in the complete graph, the number of edges is n into n plus 1 by 2. Or if you by the node system, vertex is v plus 1 by 2 and complete graph. But we see like whenever I iterate all the cases, all the possible nodes, and I am removing the case. So next time whenever I get that kind of scenario, I will not iterate any other cases. So it is a big O of n. So time complexity is nothing but big O of n. Okay. And space complexity is big O of n as well, because we're using a visited array. We're using a visited array, and sorry, yes, are using a map as well. We're using a visited array, and we're using a queue as well. So time complexity is big O of n. Okay. Hope you get the problem. As always, if you find any mistake here, please let me know so that I can rectify. And if you find any useful information or video on this topic, then also let me know so I can learn. Okay, bye bye.